Welcome to The Explainer. Today, we're going on a totally fascinating mechanical engineering journey into the hidden drama of industrial plants. We're going to uncover the invisible, highly structured engineering that keeps modern infrastructure from, well, quite literally tearing itself apart.
So you might be wondering, how on earth do massive steel pipes handle extreme heat without destroying themselves? I know, it sounds like a really dramatic way to start, but thermal expansion is actually a massive existential threat to high-pressure piping systems. Okay, let's dive into this and find out exactly how engineers solve this invisible problem.
To make sense of the whole shebang, we're going to follow a clear, 5-part mental map today. We'll start with the threat to piping systems, move into the anatomy of a bellows, then mastering pipe movements. After that, we'll look at types of expansion joints, and finally, essential hardware.
Let's kick things off right away with Part 1, the threat to piping systems.
Industrial pipes are constantly carrying incredibly hot stuff. We're talking live steam or blistering exhaust gases. This intense heat causes severe structural stress because, as we know, metal expands when it gets hot. If a rigid pipe system has nowhere to expand, the forces generated are just catastrophic. To really picture this threat, imagine 3 scenarios. In the first case, a pipe is totally rigid. It handles the internal pressure through physical tension and manages to hold together. But in the second case, let's say we introduce an unrestrained flexible joint into the system. Suddenly, that immense pressure acts as a force pushing outward, literally trying to blow the pipe apart. Engineers call this pressure thrust. So to prevent the system from self-destructing, we get to the third scenario. Engineers absolutely must install massive main anchors or specialized expansion joints to contain that monstrous thrust.
So how do we make a pipe flexible without it blowing up? That brings us to Part 2, anatomy of a bellows. This is the true mechanical hero of our story.
A bellows is essentially the flexible portion of an expansion joint. It's made up of one or more ripples, which the industry calls convolutions. The best way to think about this, and it's a brilliant analogy, is that a bellows behaves exactly like a mechanical spring in a piping system. When forces compress or pull it, it physically resists and absorbs that movement, just like a spring would.
Now, the exact geometry of just a single convolution determines exactly what the whole joint is capable of. The pitch, which is the distance between the peaks, and the convolution depth are the foundational building blocks here. They directly dictate the unit's spring rate, meaning how stiff it is, as well as its cycle life, which is simply how many times it can bend back and forth before it finally breaks.
Naturally, you might think a thicker bellows is always better for containing high pressure, right? Actually, scratch that, because a thicker wall creates a very stiff spring. Instead, engineers use this genius trick, multi-ply bellows. By nesting several really thin tubes inside of each other, they get the exact same pressure capacity as one thick piece of metal. But because each thin ply bends individually, it drastically drops the spring rate and massively increases the joint's cycle life. It's a total game changer.
Okay, moving right along to Part 3, mastering pipe movements. Let's look at the spatial physics of how these joints adapt to real-time forces.
There are basically 3 fundamental ways a bellows can move, and this brilliantly illustrates them. First, you have axial movement, that's compressing or extending straight along the pipeline. Next is lateral movement, which is essentially a shearing motion perpendicular to the pipe. And finally, angular deflection, where the joint actually acts like a hinge and bends.
But wait, there's a fourth movement, and the engineering manual delivers a very stern warning about this one. Torsional rotation or twisting is strongly discouraged. Absolutely no way. Twisting completely destabilizes an expansion joint. It ruins its ability to contain pressure and absorb movement. If there's any torsion present in the piping system, you absolutely must use specialized slotted hinges or gimbals to combat that twist.
Which brings us to Part 4, types of expansion joints. We're going to raise the complexity here and explore how different setups solve very specific spatial and pressure problems.
Take your basic axial expansion joint. It's an economical choice, sure, but it does absolutely nothing to restrain that massive pressure thrust we talked about earlier. You still need heavy main anchors in the facility. Contrast that with an incredibly clever solution, the pressure-balanced axial joint. Think about it. When you're hundreds of feet in the air, building a giant concrete anchor just isn't practical. This unit uses an outer balancing bellows to cleverly cancel out the pressure thrust all on its own.
Next up, we have the hinge joint. It firmly handles angular movement, but strictly in a single plane, kind of like opening a door. To level up from there, we use the gimbal expansion joint.
The hardware here works exactly like a universal joint on a drive shaft, allowing the bellows to securely handle complex, multi-plane bending while completely restraining that destructive pressure thrust.
Now watch how all this builds into an absolute beast of engineering, the universal pressure balance joint. This massive assembly combines multiple bellows and a system of heavy tie rods. By routing the pressure thrust as physical tension straight into those metal rods, the entire joint can move laterally and axially without transmitting huge forces to the adjacent pipes. This is absolutely crucial when you need to protect delicate, high-value equipment, like a massive steam turbine, from getting crushed by thermal pipe expansion.
But with all these moving parts and immense forces, there's a really sinister phenomenon out there called squirm. Squirm is a catastrophic instability, basically buckling, caused by excessive internal pressure on a long, multi-convolution bellows. Imagine trying to compress a really long, flimsy spring. It tends to pop out sideways, right? That perfectly sets up the vital need for protective armor.
And that brings us to our final section, Part 5, Essential Hardware and Accessories.
Let's look at the specialized gear these joints wear to survive. Tie rods are used to physically absorb and contain massive pressure loads so the delicate bellows doesn't have to. Meanwhile, pantographic linkages work exactly like mechanical scissors. They equally distribute movement across multiple bellows to keep everything perfectly aligned, even though they don't carry the pressure thrust themselves. Now, it's a vital engineering distinction to understand the difference between standard tie rods and limit rods. Limit rods do not contain pressure thrust during normal daily operations. They are pure emergency brakes. They just sit silently on the joint and only lock into place to prevent catastrophic overextension if, say, a main plant anchor completely fails.
Finally, let's look at the inside of the joint. You'd use an internal sleeve when you need to minimize flow turbulence or protect the delicate metal bellows from abrasive slurry flowing through the pipe. They're actually mandatory for high-velocity flows. We're talking over 25 feet per second for gas or 10 feet per second for liquids. They also act as a thermal barrier in extreme heat. Just remember, these liners are highly directional. If you accidentally install an internal sleeve pointing vertically upward, it'll literally act like a cup and trap liquid right inside the joint. Definitely not what you want.
Wow, we've covered a tremendous amount of ground today, peeling back the layers on how our infrastructure survives extreme physics. So, I'll leave you with this to think about. Next time you look at a sprawling industrial plant, ask yourself, where are the hidden joints silently absorbing the immense, invisible forces of heat and pressure? It really gives you a whole new appreciation for the brilliant, structured engineering keeping our modern world intact. Thanks so much for learning with me.